Hello everyone, this is John Lins. Welcome to this sections. And from previous sections, today or yesterday, we already saw what is a new function in Moldex3D 2020. So in this section, I will show you where to find it. Okay, this is the outline today. First, I will show you what is the new function, where to find a new function in pre-processing and post-processing. And then what is the enhancement of our solver, and at the end, what is the new modules support in Studio. The first one, the new function in CAD and the meshing tool. Now we have the capability to fix the CAD defects. Like we can see the picture here, like auto stitch, delete face, fill face, and I would like to show you how to use it in Studio. Okay, let's say I have a CAD geometry, and maybe it's been fixed with a CAD Doctor already, but there's still some defect. So click this check geometries. We can go to this fix geometry page, and we can find the fix tool here. And we provide auto stitch. Click this one, select the model, and give the tolerance. The program will automatically fix the free edge. Now it reduced from 1,300 to almost 200. And we have this one. We can manually select the free edge. For example, here I have those two edges should be connect together. So I will select those two edges and then give a tolerance. And the program will fix it. So with this tool, we can fix the free edge. And then we also have delete face functions. For example, I select this one, and this one will be removed. And for this one, the fill face, we can fill the hole from the CAD geometries. First, I need to select the boundary of this hole, and then press enter. The program will fill this hole. Okay, so those four functions is the new CAD fix tool we have in 2020. Okay. And in the next one, we have a new tool to create a curve. Could be extract from the edge or create a curve based on the two ends from two curves or join the curve. I will show you how to use it. For example, I want to extract the curve from the edge. So I go to the tool, and I have this one, extract edge curve, and then select the edge we want to extract the curve. Confirm, and you can see that we have a curve here. And for the bridge curve, we can first create two lines in this model. Sorry, I cannot create a line here. Yep, that's fine. I will show you the other way. Okay, this is another geometry. I have a defect from the cat, and I want to repair this surface because there's a hole here, and I want to keep the feature from along this curve, this feature line to here. So first I want to create a curve to connect this end to here. So I can use this bridge end, a bridge curve, and select two ends, this end and this end, and the program will create a curve. And now I have a full curve as a closed boundary, so I can go back to the fixed page to use this fill face. Yeah, to create the surface. Okay, so that's our new function for those curve tool. Okay, the next one is the defect, the mesh defect browsers. We can use this one to search the defects. It could be used for free edge or others, mesh defect or cat defect. For example, this is another models. You can see that there's some mesh defect. If we go to the mesh quality table, there's a free edge overlap, and sometimes it's very difficult to find them, especially when the free edge is very small. So we can now use this one to zoom in to each element, and then we can click this one to search the next defect. And it works for both of the defect list here. It also works for the overlap, for example, and also for the others. Okay. And the next one we improve is our cooling channel wizard. Now we support to mix the geometry type cooling channel and the line-based cooling channel. So like these pictures, we can create the line cooling channel, connect with a geometry cooling channels, and just generate a mesh is fully support. We don't need extra setting. The next one, what's new in the post-processing. The first one is the flatness. To use this flatness, we need to go to the result, and we can find one icon called flatness, and click this one, and then select the surface. We want to know what's the flatness. It could be more than one. Oh. For example, all those surfaces should be in the one plane. So I want to know what is the flatness. And you can see now the flatness is around 0.4 millimeters. And also we can use this deformation to see what is the warpage tendency. Okay. To leave this page, please go to the model tree and select this one, the flatness, and delete it. So we can go back to check the other result. Okay, now the next one is the FEA interface. We can now map the data from 3D to shear model, but it only supports Abacus solvers. For example, we have a simulation result. We can click the FEA interface and switch to the Abacus. And now we have extra option called Map 3D to Shear. And then we need to specify the shear model for it, for the mapping. We can check if the model is in the right positions. You can see here we have a shield models, and it is in the right positions. Okay, so okay, and then we can choose if we want to export the fiber orientation for the micromechanical interface or the initial strength, or don't select anything, just export the anisotropic mechanical properties and click this one. The program will export the data. Okay, the next one is about the solver enhancement. And now we can consider the part is half touch to the half of a mode base, and the other half is contact to the air. And to use this one, we must have a special attribute settings called mode plate. For example, you can see the models here. So in this model, I have a mode plate from the core side, from the movable side, and also a mode plate from the fixed side. And with this one, we are able to consider that the part is half contact to the mode base. If we create a model with the traditional weight, just a normal mode base, it's not possible to use these functions. And one extra thing, if we want to use it, we also need to go to the process condition setting. And in the cooling setting, we can find out there's a extra option called ejection time after mode opens. For example, the mode open time is 30 seconds here. So the part will stay on one side of the mode for 20 seconds. And after that, the part will leave the mode. Okay, then we can see what's the difference between them. Now I switch to the time that the mode is opened. So you can see that the temperature is not the same between them. The process is exactly the same, but one is with mode plate attribute, the other one with a mode base. So with the mode base, you consider the part is covered by the air after the part be ejected or during the mode open time. And this one, if we have a mode plate, you can consider the part is half contact to the mode base. Okay, and the next improvement is about the wattage. So in R17, it's not possible to consider the right wattage prediction when the process is not complete, like there's a short or the conversion zone is not 100% closed. For example, I have a simple case. Okay, you can see that one is run by, this round 3 is done by Moldex3D 2020, and round 4 is done by R17. And if we check the mesh, open the mesh line, you can see that the compression zone is not 100% closed. So there's some material left in the compression zone. If I hide the compression zone, you can see that. So when we calculate the wattage, we should consider all of them for the wattage. But in R17, it will only consider the part for the wattage calculation, which means you only consider the wattage as this one. So if we check the result, yeah, you can see that in R17 ignored the fact that there's some material stay in the compression zone. It just calculate the wattage for the cavity. But in Moldex3D, it consider that there's some material left in the compression zone, and they consider all of them together in the wattage calculations. And the other improvement is also the wattage for the injection molding. For example, if we have a short shot issues, in the past, I will say we should not take the wattage result from R17 if there's a short shot issues. And you can see that we have a short shot issues here. The plate is not 100% filled. And in the wattage calculation, the Moldex3D will consider the wattage with the short shot result. So you can see that it's not 100% filled, but it still can consider the element being filled for the wattage prediction. But in R17, it assumes the whole cavity is 100% filled, which is wrong for the wattage calculations. Okay, and let's go back to PowerPoint. And the next one, we support the local HTC setting. To use this one, we can go to the boundary condition setting, and there's one icon called heat transfer coefficients, and we are able to select the surface of part or from the insert or from the mold insert, and we can give the HTC value when the part stay in the mold or be ejected from the mold. And after the setting, we can find one's items called HTC in the model tree, and right click, we can edit. For example, I have HTC setting here with very low values, and we can run the simulation with it, and we can see that there's almost no heat, no thermal exchange on this surface. You can see that there's almost no heat exchange. Okay. And the next one is that we can consider the barrel compression, the 3D barrel compression. To use this one, we need to create a model in Rhino. We need to create a simple model as we create before, with a cooling channel, part, runner, small base, and for this one we need to add one extra items called injection unit, and for this one is a nozzle, so it's nozzle zone. If we have another component like screw, barrel, checking rings, we can import them and create the mesh. But it's not necessary if we just want to consider the barrel compression, because in current solver, in Moldex 2020, you only consider the shading, compressibility of the nozzle zone. There's the other component won't be considered. So it means there's no thermal exchange in the screw or in the barrel. So it's not necessary to build all of them if we just want to consider the 3D barrel compression effect. And after we create this model, use the same way to export this mesh, and then we can go to the studio. Create a new run, and still we select the molding type as the injection molding, and then import the mesh file. And then give the material data, process condition, and please be careful when we set up the process condition, we have to use machine mode. And then we have to make sure that we select the right machine. At least the screw diameter need to be right ones. Otherwise the flow rate might be wrong. So for example, this one, the screw diameter is 25 is not correct. I need to switch to the other one. No. Yeah, this model with the screw diameter as 18, so I have to select this one. And then the rest of the fitting is the same as the normal injection molding. And now we can run the simulation, and after the simulation we can see that in here I have the model already have the result. We can see that the material be compressed from the nozzle into the cavity. You can see that it's being compressed into the cavities. So the shielding effect or compressibility in the nozzle will be considered. So we can expect the injection pressure might be different than the case without this nozzle. Okay, next one. What is the new model we support in Studio? The first one is stress, of course, including the annealing simulations. To use this one, stress. First, we need to have the normal setting with injection molding, input, select the material, and others processing computation parameters. And in the boundary condition setting, we can add the fixed constraint. You can select the surface and set it as a fix. But I already have here. I already have a fixed constraint here, and then we can give the distance constraint or apply a force or pressure on the surface, which I already have here. Or we can click this one to give pressure and select where is the surface we're going to apply the pressure. Okay, but I already have it here, so we can always go to the model tree, right click, and we can edit. So here in this phase, I applied the pressure as a 0.1 megapascal, and then we can just run the simulation as stress. and then we can get the stretch result. And for the next one, we support RTM, and the mesh have to be done in the Rhino too. And the studio will only set up all the inputs, the material, the fiber orientations, and then run the simulation and check the result. And let's see how we set up the project for the RTM. So first we need to create a new run, and then the molding type have to be resin transfer molding. And then input the model we dumped in Rhino, and then input the ply orientation, the orientation data for the event. It should be a KPT file, which we will export the MAF file with this KPT file together when we finish the model in Rhino. And set up the material for the resin and also for the ply. And the rest is quite similar than the normal injection moldings. The feeding data, curing settings, and we can run the flow, cure, and warpage. And after that, we can see the result, like this one. Okay. Now the last one, we support emo decoration in Studio. To use this one, same, we need to create a new run. And it have to be the injection molding too. And then import the CAD file. It can be the step or MDG or other CAD file format. I have an MDG here, and this is the normal model we use in the injection molding is a cover of a cell phone and with a runner. And to use to consider this with emo decoration, we need to go to the boundary conditions and select this one, IMD film, and select where is the film. Okay, for example, I click here, the program just select this elements, this surface elements as a film region, and we can give the thickness for this film. For example, now it's 2.3 millimeters. Okay, and then just generate a mesh, and then do the final check, set up the material for the cavity and also the label, and then the process conditions, and just run the simulation. Okay, I can do the final check. In the material setting, we need to set up the material for the cavity and also for the label. And the rest of them is quite simple, as quite the same as a normal injection molding. And then we just run the simulations. Okay. That'll be all for the hands-on today. Thank you for your time.